In this video, I'm going to try to give you a brief overview of the quantum bound states. So the first thing to note is when you go in, there is this timer running, though it looks like nothing is happening. Well, that's because we're looking at a standing wave state of the finite square well, and that's the probability density. So if instead I say wave function, and I watch the real part, now we see it changing. Now, if your first thought is, hey, that seems wrong, our probability shouldn't be increasing and decreasing with time. Well, now let's look at what's happening with the imaginary part. This is a little slow. We can actually speed up the simulation. And now we can see, okay, they both seem to be moving. Huh. Well, if we go and play the magnitude, we see that the magnitude is constant. So one way that we're going to be visualizing this is be looking at the magnitude and then the phase. So the phase is kind of representing how much of it is real versus imaginary, and one way to do that is this nice rainbow. So we can turn off the real and imaginary, and that idea of motion is actually the phase. It's not really motion, it's just the phase changing, and then we see the magnitude. Now as I change my well, notice that this offset just moves the whole thing up and down. It doesn't change where our bound energies are, but it changes where the zero is. So it can be helpful to just put that at 0, because that's how we always did the math. Mouse control is hard. And then we can make it, for instance, wider. And you see, as you make it wider, the energy levels themselves change and the number changed. So if I click on a different one, we now see that the phase is changing very quickly. It makes sense that the phase is changing quickly because that's that term, e to the I theta, for our phase. But now that's proportional to energy. So lower energy changes slower in phase. Higher energy changes faster in phase. It's a party. Notice that you can configure the potential this way. So if you don't want to drag around, you can type in an offset, type in a width, and I really encourage you to write down the numbers you're using. That way, if you're discussing your results with someone and it doesn't make sense, you can come back later and say, oh look, that's because we were using different numbers here. You can go into a superposition state, and so when you click on a specific bar, you're going to get an energy eigenstate, and this is a way to actually create a superposition state. Then we can also go in and change the particle mass. Notice that here it's doing it in terms of mass of the electron, and so that would be a nice value to use. And then we can actually choose different types of potentials. Don't worry about the 2 wells and many wells. We're not using that right now. But instead, we could, for instance, go into the harmonic oscillator and see what happens there. So the harmonic oscillator is going to be something that we study soon, and the 1D Coulomb and 3D Coulombs will be relevant for instance, hydrogen, which we'll also study soon. And then there's the asymmetric well, which is looking at this kind of triangle-y shape, and we can make that wider, we can make it lower, we can make it deeper. And you can see that you now have this very different shape. But if I look at kind of each one of these, in all cases you see that the largest quote-unquote amplitude, right, the height of it, it's always largest over here, and that makes sense because that's where the potential is closest to our energy. So again, a classical interpretation is that your particle is going slower there. And you can see that then that turns into your exponential decay. Now one thing to notice is that you can see that the potential line in purple and my red line for the energy I've selected is intersecting just about at that dotted line. So if we come down here, that dotted line is actually where a sinusoidal pattern, and I can turn back on that, oh, that's awfully fast, right? We can now see clearly that there's kind of a sinusoidal-like pattern here. And I say like because our potential has this form. This isn't exactly a sine wave, and you can see that the amplitude is in fact changing. So this is a different type of function that looks similar to a sine wave, but is in fact different. But it converts from that oscillatory behavior to a decaying behavior. Again, not exactly equal to an exponential decay, because again, our potential is different. That when we solve those differential equations to have perfect sine waves and perfect exponentials, that was for a different potential. So again, we can call this oscillatory or sinusoidal-like, and then after this dotted line, it's exponential-like, or you could just say decaying. So it's very similar, but not identical. And now you can see if we just look there, functionally, it's continuous and the first derivative is continuous. And that's what we would expect. So remember that it, where that crossover occurs is where those lines intersect. And similarly over here, I can try to make this there on that dotted line. And then I need to adjust this. Okay, so that's dotted line here, dotted line there. So again, over here, you see that decaying behavior because it's a finite well here. It's not an infinite well. So this would look a little bit different if this was an infinite well right here, because then it would have to be at 0. Over here, again, there's that nice smooth crossover. So I hope this has given you a little bit of an introduction, how to use the simulation, how to find your way around. Again, to start with, it can be really helpful to just think about the square well, but I do encourage you to explore.